Yeah. Hi, everyone. So we have looked at Almo. So the last embedding that is left is BERT. We've covered word2vec, fast text, Glove, um, Elmo, and now we are going with BERT. These are the most widely used embedding techniques. Um, BERT, I think, is more an encoder technique. So preferably, it is good if we could look at it after looking at the um, transformer architecture and attention mechanism and stuff. But I'll go through it now quickly, and post that as well. I'll look at BERT on how it works and stuff. Okay. So with that being said, I should have looked up BERT beforehand, but let's me get started with BERT here. Minimize this. Before going to BERT, I just thought of doing a BERT being the last one. I thought of doing a quick study on comparison between the embedding text embedding models. I'll read through it. Text into numerical form. Text embedding allows computers to process, analyze, and interpret human language with remarkable efficiency. In this article delves into the concept, various algorithms, models, and applications of text embedding. Was transforming text data into numerical form to interactive software. Embedding scales the semantic and syntactic essence of words with documents presenting them. Potential NLP and NLP embedding separation is there. Okay. So what this is neural networks to the neural associations rule has corpus or text represents this space. frozen. It'll do. Okay, cool. Let's go to BERT.
Yeah, yeah. All eyes on you.
Today, we're going to talk about BERT. So let's jump into it. This is the Transformer Neural Network architecture that was initially created to solve the problem of language translation. This was very well received. Until this point, LSTM networks had been used to solve this problem, but they had a few problems themselves. LSTM networks are slow to train. Words are passed in sequentially and are generated sequentially. It can take a significant number of time steps for the neural net to learn, and it's not really the best at capturing the true meaning of words. Yes, even bidirectional LSTMs, because even here, they are technically learning left to right and right to left contexts separately and then concatenating them. So the true context is slightly lost. But the transformer architecture addresses some of these concerns. First, they are faster as words can be processed simultaneously. Second, the context of words is better learned, as they can learn context from both directions simultaneously. So for now, let's see the transformer in action. Say we want to train this architecture to convert English to French. The transformer consists of two key components, an encoder and a decoder. The encoder takes the English words simultaneously and it generates embeddings for every word simultaneously. These embeddings are vectors that encapsulate the meaning of the word. Similar words have closer numbers in their vectors. The decoder takes these embeddings from the encoder and the previously generated words of the translated French sentence, and then it uses them to generate the next French word. And we keep generating the French translation one word at a time until the end of sentence is reached. What makes this conceptually so much more appealing than some LSTM cell is that we can physically see a separation in tasks. The encoder learns what is English, what is grammar, and more importantly, what is context. The decoder learns how do English words relate to French words. Both of these, even separately, have some underlying understanding of language. And it's because of this understanding that we can pick apart this architecture and build systems that understand language. We stack the decoders and we get the GPT transformer architecture. Conversely, if we stack just the encoders, we get BERT, a bidirectional encoder representation from transformer, which is exactly what it is. The OG transformer has language translation on lock, but we can use BERT to learn language translation, question answering, sentiment analysis, text summarization, and many more tasks. Turns out all of these problems require the understanding of language. So we can train BERT to understand language and then fine tune BERT depending on the problem we want to solve. As such, the training of BERT is done in two phases. The first phase is pre training, where the model understands what is language and context. And the second phase is fine tuning, where the model learns, I know language, but how do I solve this problem? From here, we'll go through pre training and fine tuning, starting at the highest level and then delving further and further into details after every pass. So let's go deeper into each phase. So, pre training. The goal of pre training is to make BERT learn what is language and what is context. BERT learns language by training on two unsupervised tasks simultaneously. They are mass language modeling and next sentence prediction. For mass language modeling, BERT takes in a sentence with random words filled with masks. The goal is to output these mask tokens. And this is kind of like fill in the blanks. It helps BERT understand bidirectional context within a sentence. In the case of next sentence prediction, BERT takes in two sentences and it determines if the second sentence actually follows the first, in kind of what is like a binary classification problem. This helps BERT understand context across different sentences themselves. And using both of these together, BERT gets a good understanding of language. Great, so that's pre training. Now, the fine tuning phase. So we can now further train BERT on very specific NLP tasks. For example, let's take question answering. All we need to do is replace the fully connected output layers of the network with a fresh set of output layers that can basically output the answer to the question we want. Then we can perform supervised training using a question answering dataset. It won't take long since it's only the output parameters that are learned from scratch. The rest of the model parameters are just slightly fine tuned. And as a result, training time is fast. And we can do this for any NLP problem. That is, replace the output layers and then train with a specific data set. Okay, so that's pass one of the explanation on pre training and fine tuning. Let's go on to pass two with some more details. During BERT pre training, we train on mass language modeling and next sentence prediction. In practice, both of these problems are trained simultaneously. The input is a set of two sentences with some of the words being masked. Each token is a word. And we convert each of these words into embeddings using pre trained embeddings. This provides a good starting point for BERT to work with. Now, on the output side, C is the binary output for the next sentence prediction. So it would output 1 if sentence B follows sentence A in context, and 0 if sentence B doesn't follow sentence A. Each of the T's here are word vectors that correspond to the outputs for the mass language model problem. So the number of word vectors that we input is the same as the number of word vectors that we output. Now, on the fine tuning phase, though, if we wanted to perform question answering, we would train the model by modifying the inputs and the output layer. We pass in the question, followed by a passage containing the answer as inputs, and in the output layer, 0 if sentence B doesn't follow sentence prediction. In practice, both of these problems are trained simultaneously. The input is a set of two sentences with some of the words being masked. Each token is a word. And we convert each of these words into embeddings using pre trained embeddings. This provides a good starting point for BERT to work with. Now, on the output side, C is the binary output for the next sentence prediction. So it would output 1 if sentence B follows sentence A in context, and 0 if sentence B doesn't follow sentence A. Each of the T's here are word vectors that correspond to the outputs for the mass language model problem. So the number of word vectors that we input is the same as the number of word vectors that we output. Now, on the fine tuning phase, though, if we wanted to perform question answering, we would train the model by modifying the inputs and the output layer. We pass in the question, followed by a passage containing the answer as inputs. And in the output layer, we would output the start and the end words that encapsulate the answer, assuming that the answer is within the same span of text. Now, that's pass two of the explanation. Now for pass three, where we dive further into detail.
USAA for homeowners who being ready. That's why we have safety tips for things like fires.
This is going to be fun. On the input side, how are we going to generate these embeddings from the word token inputs? Well, the initial embedding is constructed from three vectors. The token embeddings are the pre-trained embeddings. The main paper uses word piece embeddings that have a vocabulary of 30,000 tokens. The segment embeddings is basically the sentence number that is encoded into a vector. And the position embeddings is the position of a word within that sentence that is encoded into a vector. Adding these three vectors together, we get an embedding vector that we use as input to BERT. The segment and position embeddings are required for temporal ordering since all these vectors are fed in simultaneously into BERT, and language models need this ordering preserved. Cool. The input is starting to piece together pretty well. Let's go to the output side now. The output is a binary value that the answer is within the same span of text. Now that's pass two of the explanation. Now for pass three, where we dive further into details. This is going to be fun. On the input side, how are we going to generate these embeddings from the word token inputs? Well, the initial embedding is constructed from three vectors. The token embeddings are the pre-trained embeddings. The main paper uses word piece embeddings that have a vocabulary of 30,000 tokens. The segment embeddings is basically the sentence number that is encoded into a vector. And the position embeddings is the position of a word within that sentence that is encoded into a vector. Adding these three vectors together, we get an embedding vector that we use as input to BERT. The segment and position embeddings are required for temporal ordering since all these vectors are fed in simultaneously into BERT, and language models need this ordering preserved. Cool. The input is starting to piece together pretty well. Let's go to the output side now. The output is a binary value C and a bunch of word vectors. But with training, we need to minimize a loss. So, two key details to note here. All of these word vectors have the same size, and all of these word vectors are generated simultaneously. We need to take each word vector, pass it into a fully connected layered output with the same number of neurons equal to the number of tokens in the vocabulary. So that would be an output layer corresponding to 30,000 neurons in this case. And we would apply a softmax activation. This way, we would convert a word vector to a distribution. And the actual label of this distribution would be a one hot encoded vector for the actual word. And so we compare these two distributions and then train the network using the cross entropy loss. But note that the output has all the words, even though those inputs weren't masked at all. The loss, though, only considers the prediction of the masked words, and it ignores all the other words that are output by the network. This is done to ensure that more focus is given to predicting these mask values so that it gets them correct, and it increases context awareness. So that was the 3 passes of explaining the pre-training and fine-tuning of BERT. So let's put this all together. We pre-train BERT with mass language modeling and next sentence prediction. For every word, we get the token embedding from the pre-trained word piece embeddings, add the position and segment embeddings to account for the ordering of the inputs. These are then passed into BERT, which under the hood is a stack of transformer encoders, and it outputs a bunch of word vectors for mass language modeling and a binary value for next sentence prediction. The word vectors are then converted into a distribution to train using cross entropy loss. Once training is complete, BERT has some notion of language. It's a language model. The next step is the fine-tuning phase, where we perform a supervised training depending on the task we want to solve. And this should happen fast. In fact, the BERT squad, that is the Stanford question and answer model, only takes about 30 minutes to fine-tune from a language model for a 91% performance. Of course, performance depends on how big we want BERT to be. Now, the BERT large model, which has 340 million parameters, can achieve way higher accuracies than the BERT base model, which only has 110 parameters. There's so much more to address about the internals of BERT that I could go on forever. But for now, I hope this explanation was good to get you an idea of what BERT really does under the hood. For more details on the transformer neural network architecture, which is the foundations of BERT itself, click on this video. Subscribe and stay safe. A lot more content coming your way soon, and I'll see you soon. Bye-bye.
Okay, now let's look at BERT with an example. Okay, I think this explains, but properly. Let's look at it and understand. They wrote it with example. Good. The special. So, but we'll take one or two sentences. You gives a separator token to differentiate them. It always appears at the start of the text. Then is specific to classification task. Okay. So always required. Only have one sentence. Word for classification. That's how expects to see. Okay, so the CLS token and the separator token are mandatory for the input, it seems. So the standard format is CLS token sentence 1, separator sentence 2. Sentence 2 is optional. That's what it says. Sentence 1 is input. Tokenization and word embedding. Next, let's take a look at how we convert the words into numerical representations. Word embeddings. For take the sentence and tokenize it. Sentence. Is the sentence I want. Notice how the words embedding is represented. Embeddings has been split into smaller subwords and characters. This is because BERT vocabulary is fixed with the size of 30k tokens. Words that are part of vocabulary are represented as subwords and characters. This I didn't understand. Oh, this is output token. So the tokenizer tokenizes them, and in case if there is a word that is not part of the tokenizers, 30k words, it will break it down into smaller pieces, is what it is saying. Here is the sentence. Into embeddings. That are not part of vocabulary represented as subwords and characters. Takes the input sentence and will decide to keep every word as a whole word. The subwords with special representation of the first sub. The example above. The word characters. Okay. here on we'll use the next two instance of the. So we have tokenized it. That is also correct. So BERT is trained on and expect sentence pairs using ones and zeros. Distinguish between the two sentences. That is, text we must specify which sentence it belongs to. So zeros. To process. And then the one. Mark each other. Wrong to sentence one. Segment ID is one. So segment IDs is classification on whether it is the first sentence or second sentence. First sentence is marked with 0 and the second sentence is marked with 1. In this context, as he whoever has only one sentence, they picked up one sentence with one class token and one separator token. They are going to use all ones. So token tensor has index tokens and segment tensor has segment IDs. Token tensor is this one. Index token and segment IDs. Extracting embedding. Next, we need to convert our data to input format and call the BERT model. We are ignoring of how to create tensors here. But you can transformers library example will use a pre-trained model and sets it in our mode as opposed to training mode. Stands off. We have bought the model, which is already pre-trained model. We are taking it. Model level. Next, we'll evaluate BERT on our example text and so that work. Run the text through BERT and collect all of the hidden states produced. Okay, one second. I missed on the extracting embeddings. Next, we need to convert our data to tensors input format for the model and call the BERT model. We are ignoring details of how to create tensors here. And Hugging Face and so on. Okay. Example will uses a pre-trained model and sets it up in eval mode as opposing to training mode, which turns off dropout regularization. Okay. Tokens, tensor segments, tensor evaluating model will return a different. The third item will be the hidden state. So assignment hidden states has 4 dimensions. The following are the layer number 13 layers. The first element in Number of layers 13, number of patches 1, number of tokens 22. Okay. For token, six, 10, 19, right? Yeah, 6, 10, 19. That between 10, 6 and 10, 19. So same bank, 94%, 69%. I use case of customers. What is the best contextualized embeddings for help in their context? BERT as a service on GitHub, which is intended to create word embeddings for your text using BERT and experience it with different approaches to come. Invented with different approaches to combining these embeddings and shared some conclusions on this. Now, if you keep this up at that point, it's very far and fast. Okay, good. So that's it with BERT for today. So BERT is simple. BERT has two approaches of. I mean, see, if you see word to vec, glow, fast text, Elmo, BERT, all of these, they are actually building models which solve certain problem. And while they're solving certain problem, they are actually figuring out um, in the solution of the problem, the output is being not exactly mapped as the embeddings, but um, solve when you are solving the problem, the byproduct, kind of a byproduct, is what is your embeddings. Um, like in Elmo, the bidirectional LSTMs are used, and the outputs of these bidirectional LSTMs, H like HI, HJ, um, and also the with certain weights and also some token. Together, these are kept into one equation, and then that equation's output is used as embedding. Similarly, in BERT, what they have done is they are trying to solve. They have taken two problems. Um, that is, one is mass sentence model. I think let's look at the names properly. MSM, mass sentence, and next sentence prediction, MSP. Control F. Yeah, MLM, masked language model. Sorry, next sentence prediction. NSP is correct. MLM is masked language model. So masked language model and next sentence prediction. So what they're doing is they're taking a sentence. They're taking two sentences, matter of fact. So and they are masking certain words, that are they're removing certain words within the two sentences, and they're trying to predict those two sentences. First thing. Second thing is they're also trying to see uh, uh, is the first sentence, second sentence next to each other, kind of stuff, right? Like neighboring sentences. That's more understanding of. So I think the MLM majorly contributes towards a word prediction, and the NSP prediction helps in the context prediction at sentence level, kind of stuff. So the output will be first is a token, which will be a binary prediction saying that these two sentences are next sentences or not. It will be a 0 and 1, and then next will be a list of tokens, which will also actually predict the masked words, kind of stuff. So those are the two problems that they're trying to solve using the um, bidirectional encoder transformers here. Only the encoder piece part of the transformers is being used as models. Um, what it also is doing is it is a tokenization. It has a tokenization mechanism of its own, which is covering some 30,000 words, and uh, basing on 30,000 word tokens, it is actually initially tokenizing. Like initially, to give input, you should tokenize, right? So those tokenization is used, and also is passing the segment IDs, which shows whether it is a first sentence or a second sentence. Basing on that, um, it is like the first sentence is represented by 0, second sentence is 1. If there is only one sentence, it's represented by 1, kind of stuff. So um, mm, so the segment IDs and the tokenized tokens of these words. Okay, in tokenization, if there is as it is a limited 30K set, and if there is a word which is not part of the 30K, then it is broken down into smaller words, and those combinations are used. So that's one thing. So that it is if there is an unknown word which is not part of 30K, that is also addressed. So that's one logic. And um, and these details of tokenization and the segment IDs, they are passed to the model, and the model predicts the output. Um, One thing that I didn't see in this blog that is there is masking. So the real expectation is to mask, but I think the BERT model itself takes the tokens uh, and introduce some masking and prediction in the process. So there are multiple layers that are used, to do the prediction. The encoders are repeated in multiple layers. We'll more understand more about the encoders, decoders, and the transformer architecture when we go to the transformer architecture and stuff. So there are multiple layers. Output is given in multiple layers. So there are approaches on which layers output should be considered as embeddings, right? So there are different approaches taken, but the best of the uh, um, so best of it is the last um, first second to last hidden layer is giving actually the best output kind of stuff. That's what is the end thing. So I mean, like, each layer will give some output and that output is passed to the next layer, right? So they said the finding when they try different combinations of outputs is second to last layer is the one which is giving the better output with respect to embedding. That is the finding. So that's the reason I think as a best practice, um, I, but I'm not sure if this choice of which layers output should be considered as embedding is um, is like a hyperparameter where we make a choice of it or not in the BERT training. I should look at it, but that's one of the things that is there. Um, yeah, why he says that he has chosen second to last layer is the last layer especially is focused on predicting the next sentence prediction, the class token, and it is also focused on the masked words prediction kind of stuff, right? So um, mm, but our primary target is that's actually a problem statement that we're trying to solve for language understanding and context understanding, but the primary focus is to have the embeddings of are the embedding tokens of representations of each of the words and sentences is what our target is. So that is being predicted. Word embeddings can be taken from layers, but overall sentence embedding, how it is taken, is something which I didn't understand. I'll see if I can understand more. But this is how the BERT embedding is working. Hope it's clear to some extent. I mean, to the depth it is, I would not agree it is clear, because I think after going to the transformer architecture, we should come back again here and understand how things are working in much more detail. But for now it is good, so that we can actually say that we understand BERT embedding and we know how to use it kind of stuff. Okay, so that's it for today. Then we'll cover the uh, remaining plan tomorrow. So mostly tomorrow we'll spend time on planning on the next steps with respect to POS, NER, transformer architecture, and of course attention is all you need, paper, and those things we'll cover tomorrow in so that we'll have a plan on how to cover most of them. I think NER, POS tagging and everything should be looked into it. The embeddings that we have left out is our GPT embeddings and stuff. Those are, I think, those are not open source. They're a proprietary OpenAI's embedding techniques and stuff. How far they're do we have any papers published on it? Do we have an understanding of it? We need to see. But I think these are the most used ones. GPT are more commercial embeddings that is used like before calling OpenAI. You have a you call the you can call the embeddings, and then you can generate embeddings and then use them. So that's a different service kind of stuff. Okay, so that's it for today. We'll continue tomorrow. Yeah. But good part is, for today at least, we have completed embeddings successfully on the list of embeddings that are on the top priority. We have completed all the embeddings. Maybe summary of embeddings we can go through it, or we can revise it one fine day, so that we'll cover all the embeddings in one go. Okay, thanks guys. Bye.